and he's at Tweak.io actually using Haskell stuff for industrial clients. And this is work motivated.
Thanks, Serge. So yeah, I'm going to present you something that hopefully will make Patrick's life closer. So I'd like some feedback from after the talk from Patrick and tell me, if this solves many of his problems and if you have any problems for your life. In fact, Patrick motivated a lot of, that there's a reason for why we came up with this extension. So making it my life a little bit easier. I'm sorry about the aspect ratio slides. I don't know how to fix that. So, of course, if you're starting with your laptop and you want to run computations on it, that's all well and good. But after a while, you might think that your laptop is burning your thighs, and then that's time for shipping these computations somewhere else. And if you happen to have a lot of these other computers sitting around, then what you really want is to be able to just take whatever computation is sitting around that's in scope, in your program, and just say this, send it there, and run this computation over there. Okay, not here, over there. And then of course, those other machines might are free to delegate computations to other machines and so on and so forth. There was a paper at Haskell Symposium in 2011 that presented a framework called Haskell that gave you a framework in order to do this stuff fairly conveniently. And I'll just start with a very simple way of remoting computation, where if you just have very simple primitives such as being able to send messages and receive these messages. So that's what the send and expect primitives do over here. And with these two primitives, well, so you can send messages, and the messages are structured. They're not just flat byte strings, and that's quite nice. So what's going on here is that we want to have some silly arithmetic that's done on some remote machines. But we're going through quite a lot of indirection here to have that happen. So we're defining a data type that of all possible computations that we might want to express on the remote side, and then we have the server process on the remote side that's essentially an interpreter for our set of commands. And so this is quite error prone, as I'll discuss in a minute. I just wanted to point out, for the benefit of my friend Carter over here, that Haskell gives you a lot more than just these basic primitives to send structured messages and receive them. You can also set up monitors on these other machines that you're using to run your computations, and you can have you can set up these monitoring hierarchies that are actually quite nested. And this is a pretty nice way to recover compilers, which are ripe in a cluster of any scale. So as I said, so far we have a way of having other computers do computation for us, but it's quite indirect. It's error prone because I may make a mistake in my interpreter. It's difficult to extend because every time I want to have a new computation, well, I have to extend my interpreter. And then it's also anti-modular because everyone has to share this one module where the commands are defined on the interpreters. So hopefully we can do better than that. And ideally, what we want to be able to do is to just say, well, I happen to have these functions that are lying around. Just send them over to the other side, just as I would in some other languages that allow distributed programming. So this is direct. It's error-proof, easy to extend, and it's a lot more modular because I don't have this global type of all computation. And you'll notice that I don't have the right-hand side. I don't have this interpretation processing. But hold on a sec. We just in the previous slide, we're basically allowing to be able to send arbitrary closures, but that's not really what you want. For one, in order to do that, you would need specific support in GHC to be able to so serialize all the closures no matter what's in them, and send them across to the other side. But in general, there's all these gnarly things that are hanging around in closures, such as I/O refs or sockets or other system resources. And you really don't want to send those on the other side in general because they won't make sense to the other side. So what we want to send instead is, what we want instead is to send only certain types of closures. And these closures are closures that, and hopefully we can get the type system to rule out that there's any of these gnarly things in the closure that we're sending to the other side. Okay? So, I'm just showing here the very basic representation of closures that we use in Cloud Haskell. But the specific representation of closures that we use doesn't really matter. In fact, we could use a much more elaborate one, such as the one that Patrick just presented. And much of the rest of the part still would be invariant to that. The important point here is that you deep within these closures. So closure is a pair of like a code pointer normally and an environment. And so we have a data type for naming code, and if you have the data type for naming code, then you can start closure. This is the static data type, and so basically what this extension is going to be about is going to be getting the compiler to give us these pointers to code when it's appropriate to do so, and rule out those cases where it's really not appropriate to do so. So that I don't have to generate these things.
You mean on the line that says code pointer, you mean static of n valor?
Right. So that's what I have here. Yes. Yes, and so Patrick already explained a lot of reasons why. So we want environments that are serializable. And one very easy way to ensure that is just to say, well, my environment is a byte string. It's the serialized encoding of my environment. And then the code that we're pointing to is code that will be able to recreate a closure given some environment. Okay. And these two things are serializable, so now I can send these things over to the other side of the network, independently of the actual code that's being referred to here. All right, so we can wing all of this in Haskell, as Patrick already mentioned. Template Haskell, as Patrick's already mentioned. It's pretty clunky. What I'd like to point out first and foremost is that the template Haskell solution ultimately ends up being very anti-modular, once again, because you have to build up manually these tables of that map names that we introduce for pieces of code to the actual code itself. And so you'll have one of these tables for each module, and then you have to somehow combine these remote tables for each module into one global one for the entire program. And this is very anti-modular because without a module, then, or you add a new module to your program, then you have to modify this big remote table. So we can do better, and this is what this is all about, where the idea is that we introduce a new keyword, one keyword, it's a static keyword, and basically what it's saying here is that we're grabbing a pointer or a name for the expressions that appear as in the body of this new syntactic form. And then, so given given the static, we can lift this to a closure, and then we can just send that to the remote side. Again, no interpretation going on. This is a very direct way of sending computation. It's just as before. Right. So when can I take the when can I ask for a name or a label for an expression? Well, essentially, whenever these expressions are closed. So here, I'll just distinguish between what's in the global environment. That's a top-level definition, so that's going to be a delta. And then I have things that are in gamma, that's kind of my local environment. And I'm basically saying you need to be able to type E in an environment that only has global definitions, nothing local. Okay. So what's the operational semantics for these for this new syntactic form that we just defined? The idea is that if you have static E appearing in any context, then what that really means is that what the compiler is going to do behind your back is he's going to introduce a new top-level definition using a new fresh name. Let's just say F. So the definition of F is going to be the body of the static compression, and then in place of the occurrence of the static form, we just stick in a name. It can be an arbitrary name. All we care is that it's a name that's going to be unique across the program, so that the remote side can uniquely identify which function you meant when we're sending that. Okay. This is as far as the paper that was presented in 2011 went, and conspicuously, the paper didn't discuss what happens when you have polymorphic types. And as Patrick mentioned, this is actually really quite nice to have. And I'll just motivate that with a very simple example. Say you want to do RPC calls. So you're going to, you can do this with a combination of send and expect and so on. But really what you'd like is to have a function that the library gives you, call, that combines these two things and does a bit more on top. So really, what does call need? Well, so call needs to know where you want to send your RPC call to. It needs you to provide a function that's going to, or an action, a process monad that's going to yield some value, type A. But this value of type A, we need to know how to send it back across the network to you. We need a serialization dictionary. But we also need to be able to send that dictionary to the remote side. So we need to make that static. Okay, so how would we implement call? Well, we want call to work for any type A. And so with our extension, we would use static so basically what we do is we take the function that we want to send to the remote site, and we would compose this function with something that sends back the value across the network. Serializes it and sends it back. And so how we do this composition with the bind CP combinator. If you look at the definition of bind CP, you see the occurrence of the static keyword here. We're basically taking the bind operator, and we're saying that we're going to apply it to CM and CK and send that over. But if you notice here, actually the bind operator. So here I'm writing things out in a kind of simile system F. And you'll notice that over here the bind isn't actually closed, right? Because you have A and B that are type variables, and they're appearing free in the expression. So what gives? Well, one would argue actually that in GHC, types don't matter. You have a phase distinction, and so actually these A's and these B's, they're static, and so we modify the typing rule that we had earlier, and we say, well, so actually, we're going to drop gamma. This is the local environment, but not everything in gamma. We're just going to drop. We're going to keep the type variables because those are morally static. Okay, so where are we from here? We've implemented. We have a first implementation, which we have to now refactor, simplify, and so there's a lot of change to make, and we're working on that assignment. We have a first implementation. One big problem that we need to solve is how to solve self-faults, and you can ask me about that during the questions. I'd just like to also say that I believe that this extension is really complementary to other approaches to remoting computations, and you shouldn't think of this as mutually exclusive. I'll stop there. Thank you very much.
Okay, questions?
How does that interact with, say, global mutable variables, or if you use, say, perform IO to read an environment variable? Is that allowed by the static keyword?
Probably not.
Well, so the point is that you can, so if you use unsafe perform IO, then you're probably going to trick me into sending stuff that everybody should send.
That's what I'm trying to understand. So if I have the top level thing that read an environment variable and it's going to be different on two different machines, both running Cloud Haskell, I could trick the system that way. You're saying?
Possibly.
Okay.
That's what unsafe perform IO is for.
Yes. Exactly. I just want to understand how unsafe it is. Okay.
So it's very unsafe.
Maximally unsafe.
Right. And in fact, so in the current state of things, you can actually cycle the machine by just a remote machine by saying, here, have a function of type int arrow int. But actually, the function is a completely different function of a completely different type. You just send it over, say, well, so you're basically lying about its type, and then the remote side is going to cycle. So really what we need is we need a way to basically attach somehow type representations for functions along with their labels, so that when you're looking up the label, when you're resolving a label to an actual function, then you also check that it has the expected type. Because right now these types they're thrown away; they're not in the binary, so we have a way to check that.
Is there a way to give maybe slightly richer semantics? I know it screws up transparency a bit to labels, other than just saying that they're quote fresh. Like, so are they the same between compiles? Would be they be the same if I compiled the same source tree precisely twice on two different machines? Ideally, what I would like would be a label that would be the same for the function of that name and that location in a sort of module hierarchy in some decent way, because maybe I want to sort of swap out a binary to hotfix a bug without having to take down everything else that likes to talk to it. And I know that loosens up the semantics in a tricky way, but I feel it would make it even better.
Yes. So right now you can't, we don't show you what's actually in the static, right? It's completely opaque. So if you don't know what it says, you can compare it.
You can keep it opaque. I just want to know if you could make me promises about it, despite it being opaque.
So with the original, okay, so this is work in progress, and the original world in which you're setting yourself when you're using Haskell is a world where everyone has the same binary, and so in this happy world, then there's none of the problems that you mentioned. But certainly these are going to pop up once you do stuff like hot patching and so on, and
multi-architecture systems.
Right, and then we need something like that.
So, from reading the static value patch, my understanding is it sort of gives both the module and it's like a triple of the module packaging and like a top level variable, or at least that was the initial design iteration of that.
Right.
Duncan and I myself have a quick question.
So I'm afraid we have to stop now. Skip lightning talks at the end. So if we
Keep going.
lightning talks, yeah, take the rest of this offline.